Welcome, class. We are going to talk about Chapter 6. Now, Chapter 6 has some abstract and a little bit mathematical foundations for understanding stability and convection. But in order to talk about thunderstorms, tornadoes, and hurricanes eventually in this course, we really do need to understand these concepts. And it all has to do with air rising and creating clouds, which eventually, under the right conditions, can create thunderstorms. So we're going to talk about what an adiabatic process is and how that is linked to buoyancy and stability. Now, you probably have heard of buoyancy, but stability is a very important but somewhat difficult concept to understand. So we're going to try to get through this. Then we're going to look into how the atmosphere is lifted, what stable, unstable, and conditionally unstable mean, and then how clouds develop in unstable atmospheric conditions. These are key terms. We just talked about adiabatic and buoyancy and stability. We'll get into lifting mechanisms and various adiabatic rates, know what stability, or I should say stable, unstable, conditionally unstable mean, and all these other terms as we go along. By the way, I mentioned this in an earlier lecture, but one of the ways that we assess stability is using a radiosonde. And the radiosonde is actually this contraption right here, and we link it to a helium balloon and we let it go and it samples the vertical part of our atmosphere. Okay, so let's take a moment to talk about pressure again. Atmospheric pressure is very high near the surface, so you could think of again as atmospheric pressure is the number or the amount of atmospheric particles or molecules above you. But as you get higher and higher into the atmosphere, as you know already, it thins out. Just like going up, on a pretty tall mountain, we can talk about Big Bear or Mammoth, it might be harder to breathe when you're up there because the air is thinner. Well, another consequence of that is that if we have a bubble of air like this, it acts like a balloon. And as it goes up, the size of that parcel of air also increases because there's less pressure as we go up into the atmosphere. This is how helium balloons eventually pop and fall down. They rise through the atmosphere, and then the size of the balloon gets bigger and bigger and can only be so big before it pops. So within that parcel of air, it has a constant cooling rate. And that cooling rate, as it goes up, we call that adiabatic rate. And the term adiabatic means that there is no exchange of heat or temperature between a parcel of air, like this one, and then the air around it. This would be the air next to it. Now, if it's a dry parcel, meaning that it's not a cloud, this parcel has not reached the dew point, then the cooling rate is 10 degrees Celsius per 1,000 meters or 1 kilometer. For example, we have a parcel down here of 32 degrees Fahrenheit, 32 degrees Celsius. It rises to 1,000 meters above the surface and it has cooled down to 22 degrees. It rises now to 2,000 meters and it's 12 degrees Celsius. And then that would keep going and going. Remember, as it goes up, you have less pressure. Because of that less pressure, the temperature inside that parcel actually cools down. And again, given that there's no heat exchange between these bubbles or parcels of air and the air around it, which is what we're going to assume, then the temperature is decreasing or cooling 10 degrees Celsius per kilometer or 1,000 meters. Now, if a parcel of air cools down to the dew point temperature, then a cloud starts to form. So in this example, we have 32 Celsius once again. That's a pretty warm temperature in Fahrenheit and Celsius. And it cools down 10 degrees Celsius, 10 degrees Celsius, so 10 degrees Celsius here, another 10 degrees Celsius here, another 10 degrees Celsius here. But now it's a cloud. And this is the base of the cloud. And this is basically how clouds form. This beginning of the cloud, the base, is called the condensation level. Sometimes we consider it the lifting condensation level. Now, if a bubble of air inside a cloud starts to, or I should say continue to rise, it rises at a cooler, or I should say less rate. Not a cooler rate, but at a lesser rate. And it's anywhere between 5 to 7 degrees Celsius. To keep it simple for now, we're going to maintain that it cools down 5 degrees Celsius per kilometer. So that's why you see a 2 degrees Celsius here, and then after another 1,000 meters of uplift, it is cooled down to only -3 degrees Celsius. Another 1,000 meters, -8 degrees Celsius. Once again, this is the, we start with the adiabatic rate when it's not a cloud, which is considered the dry adiabatic rate. But once it reaches the dew point, then it cools at what's called the wet adiabatic rate. Sometimes that's called the moist adiabatic rate, just depending on what source you're looking at. So, buoyancy and stability. How does this play? Okay, so buoyancy, we'll define buoyancy and stability in a little bit. But you might be wondering, why does air rise? Gravity likes to keep most objects near the surface of the Earth. So what causes air to rise? Here's the biggest reason, and this comes into play when we talk about stability. Temperature differences between the parcels and the air around the parcels. Those temperature differences lead to density differences. So basically, the objects that are more dense try to stay at the surface, and the less dense particles, objects, will float, especially if it's less dense than the air around it, will float up into the upper parts of our atmosphere. You could kind of think about this as a pool. Think about a pool of water, your swimming pool. If you put a bowling ball in that swimming pool, where is it going to go? It's going to go to the bottom because a bowling ball is more dense than water. What if you put a beach ball on top? And just for argument's sake, let's say you smash that or you push that beach ball all the way to the bottom of the swimming pool. What's going to happen when you let it go? It's going to go right back up to the top because that beach ball is less dense than the water around it. This is the same concept here, but instead of talking about water and beach balls and bowling balls, we're talking about air parcels of different temperatures within the fluid of our atmosphere. Another way air can rise is through mountains, which we'll talk about later. Mountains, when air hits a mountain, it is forced to rise. So another way to think about this is a hot air balloon. I don't know, maybe you have been on a hot air balloon ride. This is something that I would like to do someday. But why do these hot air balloons rise? The answer is they are heated. So there's a heating contraption at the bottom of these balloons, and when you heat up these balloons are warmer basically than the air around it, so it makes it less dense. So that's why it goes up. And in order to go down safely, you gently let go of that heating contraption, whatever they actually use in there, and it cools down and it goes back down to the bottom of the atmosphere. You can think of parcels as helium balloons. Air does not mix very well, so there are these separated bubbles of air that can rise because they're warmer than the air around it. This is the root cause of getting a thunderstorm or getting a cloud that will rain, and also severe weather, which we'll talk about later. Okay, so let's take a look at this in a different way. Once again, we often start by separating pieces of air into air parcels. And an air parcel will have gravity, which tries to push it downward, and then this buoyancy force that allows air parcels that are less dense to rise. Now, higher density air parcels will tend to sink and hang out at the bottom, but lower density air parcels will want to rise. And what do you think is going to happen to this lower density air parcel? Remember, we have lower air pressure as we go up. So the size of this, just like a balloon, will increase. So to make this a little bit more simple, we are going to, instead of talking about density directly, we're going to just talk about temperature. So colder, now the key word is colder air will sink, meaning that this is colder than the air around it. Warmer air, which is warmer than the air around it, will rise. Okay, so let's take a look at that's just one way the air will rise, and we'll come back to that because that's the most complicated way for air to rise, is through density and temperature differences. And this heated surface, where air actually is warmer here because the surface is warmer, is one way that air will rise. And then if it reaches the dew point, it'll create a cloud. And if it continues to rise because it's warmer than the air around it, it can create a cumulonimbus cloud, a thunderstorm cloud. So we'll come back to this. If air hits a mountain, it is forced to rise. It cannot go through the mountain. So that's another way for air to go up and create clouds and severe weather. Often around here, well, I should say the deserts of California, Southern California specifically, during monsoon season, we'll see more thunderstorms than the areas that aren't mountains. You can also have a low pressure system with air rising. We'll talk about that later. And then even later yet, we'll talk about warm and cold fronts that cause air to rise. Also, so this is a little bit more complicated way. Air sometimes will converge, just like a low pressure system. Air will converge, and that air has to go somewhere. It doesn't go down into the ground. It has to go up, and that creates clouds and potentially thunderstorms. If you can tell here, this is the state of Florida in the summertime, and there are a lot of thunderstorms. In fact, almost every day in the summertime, Florida, especially Central Florida, will have a thunderstorm. Part of that is due to converging sea breezes. There's the Atlantic Ocean creating a sea breeze here, and then there's the Gulf of Mexico creating another sea breeze. They converge in the middle, cause air to rise, and potentially create thunderstorms. Okay, so stability. The point of stability is to understand what the atmosphere will probably do. So think of the word stability as a state of equilibrium. We have this rock right here down in a valley. If a person tries to push this rock upward and then suddenly lets go of that rock, where is it going to go? It goes right back down to where it started. We call this a stable equilibrium. In other words, it wants to stay where it is, but if something tries to push it elsewhere and that something goes away, then then it goes back to its initial position. However, unstable means that it won't take much for it to go somewhere else. So we have this rock on top of a hill, push that rock down the hill and it just keeps on going, and it's not going to go back up. What does this have to do with the atmosphere? Stability in the atmosphere is the state of equilibrium, or the chance for the air to move vertically. Warmer air that's warmer than air inside that parcel, if it's warmer than the air around it, we consider that an unstable condition. If the air parcel is cooler than the air around it, then we consider that a stable position. And unstable and stable conditions lead to different kinds of weather. So what do we do to figure this out? We compare the air parcel's lapse rate, which are, there's two of them really, and they're fixed, and then we compare that to the environmental lapse rate, the air around the parcel, which changes from day to day. So let's take a look at some examples. Going back to the concept of air parcel, remember, warmer air wants to rise. So if we have a condition where the lapse rate here is, different, or if the air here is warmer than the air around here, at each moment that the air is warmer than the air around it, it's going to continue to rise. And it might stop rising if the temperatures between the two pieces of air are the same, because therefore then it's not warmer anymore. And we would probably have see if I can write here, unstable, I've never done this before, unstable conditions here. However, with colder air, this air is colder and more dense than the air around it, so it wants to go down. We typically have stable, here we go again, stable conditions. And just to keep it very simple for now, unstable conditions is what we want if we want thunderstorms to form. Stable conditions typically mean that we have clear sunny days, not conducive to thunderstorms. Okay, so sort of as a repeat, because these concepts aren't necessarily easy to understand. Clouds tend to form when air rises and then cools. Okay, so think about this for a second. Air rises because it will be warmer than the air around it. But as it's rising, it's also cooling. But so is the air around it. So it's really all about the comparison. Remember, adiabatic processes mean that the air inside that parcel is not mixing with the air around it. And in nature, that really does happen. So inside the parcel, if it's dry, it cools at 10 degrees Celsius per kilometer, or 1,000 meters. And that means that it's not a cloud, so the relative humidity is less than 100%. It's moist or wet if it's a cloud, and then it cools only at a rate of 6 degrees Celsius per 1,000 meters. And that's when it's a cloud. And remember, a cloud means that the relative humidity is 100%. So we already know the lapse rates of the parcels. We do not always know the lapse rate outside the parcel. So what we have to do is basically launch a radio song with that helium balloon and figure out what the lapse rate of the environment is. That's the thing that changes from day to day, or even from different parts of a day. So again, we do not know this unless we launch a weather balloon. So going back to my figure or picture here that I showed before, this is one way that we do this. And figuring out whether or not the atmosphere is going to be stable or unstable is used almost exclusively in times where we believe there are going to be thunderstorms or severe weather, because thunderstorms form in not just unstable atmosphere, but really unstable atmosphere. And so thunderstorms are basically the attempt to make an unstable atmosphere become stable again. It's all about nature wanting balance. What does this mean for you, and how do we assess stability? Okay, we have three stability conditions. The first one is absolutely stable, which basically means that the environmental lapse rate must be less than the wet adiabatic lapse rate. So that also means that the air around the parcel will cool at a rate less than 6 degrees Celsius. And this happens a lot here in Los Angeles because the Pacific Ocean, which is generally cool, will create a cool layer at the surface, but above, especially in summer, we might have warmer air. Now that makes sense, right? Because warm air likes to rise and cold air likes to sink. So if cold air is already at the ground and warm air is above that, that's a pretty stable environment. The atmosphere likes that because it makes sense. And when that happens, we don't usually get clouds. We usually have these, nice sunny days in Los Angeles. Unfortunately, as a side note, stable environments also can lead to smog because there isn't a lot of movement. There aren't any parcels moving up or down. Now, if we realize after we launch a weather balloon that our environmental lapse rate is actually greater than 10 degrees Celsius per kilometer, then we have unstable atmospheric conditions. Around here, this doesn't happen very much, but it can sometimes in the summer if we have monsoonal influence, and sometimes in the winter when we get our winter rain. So because we have warmer air at the surface and cooler air above, that doesn't make sense, right? Because that warm air is less dense and the cold air above it is more dense. No, it shouldn't be. The air should not get denser as we go up. It should get less dense. So thunderstorms are sort of the attempt to make sure that the cold air stays at the bottom and the warm air stays aloft. But to keep it simple for now, air will want to rise and will create vertical clouds, and we will get thunderstorms and potentially severe weather. Now we also have this sort of middle ground. Remember, with stable conditions, the environmental lapse rate had to be less than 6. With unstable, it had to be greater than 10. Conditionally unstable means it's somewhere in between. And the environmental lapse rate, the air around those parcels will cool somewhere between 6 and 10. And basically that means that it's stable if it's not a cloud, but once it becomes a cloud, it is unstable. This is actually the typical state of the atmosphere around the world. Most of the time when we get thunderstorms, we do not have absolutely unstable conditions. We usually need some form of lifting mechanism to cause air to rise and become a cloud. But then once it's a cloud, it will become unstable and it can continue to rise. And if it continues to rise all the way up to the top of the troposphere, that's when we get our thunderstorm cloud, our cumulonimbus cloud. Now this is a lot of information. There is a lot to think about when it comes to figuring out stability. But to keep it simple, most of the time, and I cover this stuff in both my physical geography courses and my regular meteorology courses, we use a chart. And this is a sort of a simplified version of that chart, where we have altitude, which increases here on the side, and we have temperature that increases as we go to the right. Then we plot our various lapse rates. We have 10 degrees Celsius per kilometer, which represents an air parcel's lapse rate as we go up if it's dry. And then, like I said, sometimes it's 5, sometimes it's 6, sometimes it's 7. I know earlier I used 5, and this time we're going to use 6. The reason is the wet adiabatic rate depends on actually how much moisture there is, but we'll talk about that later. And so this is the lapse rate if it's a cloud. So honestly, this can be very simple. All we really need to know is what is the environmental lapse rate. In the real world, we would have to launch a weather balloon with a radiosonde. But in this class, or in my meteorology classes, I would give you the environmental lapse rate. I will tell you what it is. And then, based on that, you can tell me whether the atmosphere is stable, conditionally unstable, or absolutely unstable. This is how this works. Let's say I tell you that the environment cools off at a rate less than 6. So let's say I give you a rate that is 2. Because that's less than 6, you can assume that it's absolutely stable. The air isn't going to move vertically very much. If I tell you that the environmental lapse rate, let's say, is 12, which is greater than 10, then you just assume that the atmosphere is absolutely unstable. And I wanted to show you, I talk about conditionally unstable, which is something that I think I'll skip in this class, but just to be complete, if I would tell you that the lapse rate is somewhere between 10 and 6, then you can assume conditionally unstable. So this table here kind of summarizes that. If the environmental lapse rate is greater than 10, it's unstable. If the environmental lapse rate is less than 6, it's stable. There's also neutral conditions, which I don't really cover. And then the conditionally unstable, which I just talked about, is also important. But again, I think for this course, because we're really focused on the unstable part, we're going to stick with unstable and stable. This is the key here. Okay, let's take a real-world example here. So convection basically is the process of air rising. And one of the ways that air can rise is that there is differences in the way land heats up. I talked a little bit about albedo in chapter 5. So just think about this. Let's say there's a large parking lot with cars and asphalt surrounded by grass. How will the air warm up over the parking lot compared to the grassy area nearby? Basically, the parking lot will absorb more energy, more of the sun's energy, and will heat up the air above it to a warmer temperature than the air around it. So then, that bubble of air, which you could think of it as this part right here, will rise. Now, if there's enough moisture, and let's say, I don't know, the dew point we have a certain dew point value, it'll continue to rise. Let's say it just continues to rise. And once it cools down to the dew point, which is right here, we reach the condensation level. Sometimes it's called the lifting condensation level. So here's solar heating. It's warming up a piece of the land, and that air above it is warmer. So it's going to rise. It's kind of like a lava lamp. I don't know if you guys know what a lava lamp is, but there's wax inside that lamp. Pieces of wax that are hotter than the wax around it will rise. You can actually watch that. So this is a thermal, or an piece of air that's rising. Remember, as this bubble of air rises, it expands and cools down. And if it's not a cloud, that rate is 10 degrees Celsius per 1,000 meters. But now, the dew point has been reached, so the relative humidity is 100% and we get a cloud. Now, if it continues to rise, when it's a cloud, it cools down at a rate of anywhere between 5 and 7 degrees Celsius. To stick with the chart that I showed you, we're gonna keep 6 degrees Celsius. And if it maintains that these cloud parcels are still warmer than the air next to it, if it's warmer, it will continue to rise. And in severe weather, or just thunderstorms, this will continue to rise all the way till it hits the stratosphere. Okay, summary, because again, this is a lot of information. Unstable air likes to rise until it's stable again. And sometimes it doesn't become stable until it hits the bottom of the stratosphere. That's when we get our severe weather, or at least a thunderstorm. And air will rise on its own if the environmental lapse rate is greater than 10 degrees Celsius. That makes it unstable. If it's moist, that means eventually it's going to reach the dew point and the relative humidity will be 100%. And that's how we can get really tall thunderstorm clouds. On the other hand, if the air is not warmer than the air around it, it stays put. Or if something makes it go up for a minute, like a cold front or a mountain, the minute that lifting mechanism goes away, it goes back down to its original position. And this happens if the environmental lapse rate is less than 6 degrees Celsius. Stable air leads to clear sunny days, which honestly is one of the reasons why most people love living in California. Except for meteorologists, they like more interesting weather. Here is just an example of various clouds that have different heights, because at some point at the top of that cloud the air became stable again. These did not rise all the way to the top of the troposphere or the bottom of the stratosphere. Okay, so one of the things that storm chasers actually look at is they look at a few indices, like there's index values that help us understand whether or not we're going to get severe thunderstorms. I want to highlight two of them that are really important. We have Li, or the lifting index. We also have CAPE. And the lifting index is just basically taking the temperature of the environment at about halfway up the atmosphere, 500 millibars, and minus that temperature of the parcel. Basically, if we get large negative values for the lifting index, we have an extremely unstable situation where severe thunderstorms are probable and maybe even tornadoes. CAPE is basically the area of positive buoyancy, and it's derived, yes, don't worry about it, I'm not going to make you do calculus, but if you are a meteorology major, you will have to know calculus eventually. But basically it's just the area on a what we call a sounding graph. And I'm not going to get into the details of that, but basically the higher those values are, the higher the value of CAPE, the more probable that we're going to get severe weather and tornadoes. So this is one of those soundings that we use. There's skew T diagrams, whatever you want to call that. And lifting index is really easy to calculate. Basically, you go up to 500 millibars. You look, and this here is plotting the environment and then plotting the parcel. And you look at the differences in temperature between the parcel and the environment to calculate lifting index. And then this area between the parcel and the environment, you add up this entire area between here, that helps you get CAPE. You will not have to do this in this class. I just want you, just for completion and for my majors, I just want you to know that when you're dealing with severe weather, whether you have to forecast severe weather or you're going out and storm chasing, these are some tools to give you ideas of where to go and whether or not it's a good day to go out and chase storms. I hope you learned a little bit more about why stability and adiabatic processes are important for severe weather, and eventually we'll look much more in detail into severe weather. Thank you and see you next time.